Hello, everyone. This is Leah Freeberg from Fluke Reliability, and thanks for joining us for this Best Practices webinar. You probably know Fluke as a test tools provider. You may know that we produce some of the industry's favorite reliability tools, from infrared cameras to vibration meters, but you may not know that many of the measurements that our tools collect now can flow automatically into EAM systems of record. It happens via a framework that we call Fluke Connect. Our goal at Fluke Reliability is to better connect asset management data and teams with asset management systems to drive connected knowledge. So that's why, and of course, that knowledge depends greatly on best practices in condition-based maintenance. So that's why this series of webinars explores reliability maintenance strategies, and that's why we feature speakers from a variety of expert backgrounds. Before the presentation, we have a few housekeeping items to go over. Today's session is being recorded, so your phone lines will be muted to minimize background noise. We will be answering questions during the presentation after each speaker, as well as at the end. So please feel welcome to submit questions as we go. Take a minute now and find the questions tool in the GoToWebinar dashboard. I will share as many of your questions as time allows for our presenters to answer, and if we have unanswered questions at the end, we'll follow up with written answers. If you would like to receive the slides from today's presentation, please let us know during the survey that appears at the end of the session. So don't hang up until the survey appears and you've answered the questions. We're also happy to send you a certificate of attendance after today's webinar. You'll see a question on the survey about getting a certificate. Answer yes, and we'll send one to you. A recording of this webinar will be available on the Excelix.com website within a day or two. And that is it for housekeeping. So now for the main event. Today, we are very pleased to have with us 4 experts on integrating machine health data into your CMMS. Michael Mills, Mike Ciocys, Brian Harrison, and Jeremy Go. They will be presenting on getting more value from your CMMS Part II, integrations for improving machine health. So let's start by introducing Michael Mills. He's a senior solution engineer with Fluke Reliability. He focuses on CMMS and EAM and condition monitoring software, sanitization software, and Fluke's IoT devices. His CMMS and EAM experience stems from years as a customer success manager, solutions engineer, subject matter expert on integrated systems, and providing solutions for workplace safety, packaging, life science, manufacturing, public sectors, and utilities. So welcome, Michael, and thank you for being with us today.
Yep, good afternoon, good morning, everyone. I'm happy to be here for part 2 of our session in our webinar series.
Indeed. And if you missed part 1, that is now live on Excelix.com. Moving on, Mike Ciocys is the ProofTechnik US Technical Service and Support Manager for Fluke Reliability. His ProofTechnik career began during college in 2009 as a member of its co-op program. After time as a senior alignment engineer and an application engineer, he was promoted to his current role in 2016. He launched the technical support department in 2016 and continues to manage it. Mike obtained his Cat 3 Vibration Analyst certification in 2019 and his Certified Reliability Leader certificate in 2016, and he holds a bachelor's degree in mechanical engineering from Temple U. Welcome, Mike, and thanks for being with us today.
Well, glad to be here. Look forward to it.
We've got quite the team today. Brian Harrison is the industry IoT leader for Fluke Reliability. He has more than 10 years of experience in enterprise asset management, applying best-of-breed solutions in current industry practices. He's worked on enterprise projects across industries, including the public sector, manufacturing, and aviation, deploying a blend of EAM, mobile, and IoT solutions. He has delivered high-value projects leveraging reliability-centered maintenance in support of ISO 55001, CBM, and ICM. Welcome, Brian. Thank you for being with us today.
Happy to be here, Leah. Thank you.
Absolutely. Jeremy Go is a solutions engineer with Fluke Reliability. He joined Fluke in 2017, specializing in software management systems and condition monitoring tools. He has worked closely with Fluke Reliability's electrical and vibration tools and sensors, as well as software management, participated in several internal startup and innovation teams, and holds nearly a decade of experience in the software management space. Thank you, Jeremy, for being with us today. Really appreciate it.
Yeah, good morning. Thanks for having me.
Absolutely. All right, Michael, why don't you take it from here?
Sounds good. All right, and thank you very much, Leah, and thanks to everyone who's taking the time to join us for part 2 of our 2-part webinar series, getting the most out of your CMMS, including integrations for improving machine health. As a recap for last week's session, we discussed a few applications and use cases within a CMMS that help to drive value to the bottom line of your organization, as well as promoting user experience and satisfaction overall. So anywhere from effectively tracking warranty documentation to also infusing mobile maintenance into your maintenance strategies. We wrapped up that session speaking about integrating condition monitoring data into your existing CMMS workflows to trigger work and notifications. And to backtrack that even further, we looked at the status of automation and condition monitoring as a whole. Really, we took some time to reflect on where we're at today and what are some of the biggest showstoppers when it comes to integrating data into your work order management processes. And as it stands, results have shown that predominantly calendar-based routes and inspections are still heavily used to complete condition reviews and to complete scheduled servicing of assets. And the fact is that this strategy can be effective and establish a higher and safer floor for your operation without any real upfront investment. However, from that session, we talked about how this is an example of disconnected data with an opportunity for errors in transcribing this information and also running the risk of siloed information where potential failures and anomalies may be detected after they could have the most cost-effective outcomes for your company. So that brings us to the main purpose of today's session, a deeper discussion into how integrating metered data into your CMMS can improve machine health. Within Fluke Reliability, we commonly speak about the term connected reliability. And connected reliability is the simple concept that all systems, machinery, and people should be able to easily and effectively communicate with each other by bridging the gap between people and databases or assets and maintenance and reliability teams. And this diagram you see on your screen really shows how these parts of our ecosystem integrate and work with each other. And the vision here it's pretty simple. Unite the 3 key elements that every plant has to manage: their asset condition data, the asset management systems they use, and their maintenance and reliability teams. And the idea is to unite them in such a way that failures can be anticipated and the right actions can be performed at the right time, thus eliminating unplanned downtime and operating more efficiently. The first step in creating this type of framework is connecting asset condition data to your enterprise systems, or most commonly, your CMMS. So today, we're going to focus on the areas to the left and to the middle of your screen, which include your data connectors and how this information gathered can be aggregated and enriched by integrating this data, again, with your system of record. Okay, and using this information to advance software functions and predictive analytics. So today, again, to advance on last week's webinar, I had 3 of my colleagues who are really subject matter experts who specialize in different data connectors that exist today within the Fluke Reliability ecosystem. And also, these systems also have existing integrations with the Fluke computerized maintenance management software. And with that, that brings us to our first audience poll of the day. Leah, you would like to take it from here?
Absolutely. So some of you will have experienced this before, but I'm about to share a poll that you should be able to answer. If you cannot click the radio buttons, then just reduce your screen size back down. But our goal is to have everyone answer which one of these applies to you. So the question: how important are CMMS integrations to your maintenance processes? Option 1, very important. We already integrate 1 or more solutions. 2, important. Our integration planning is underway. 3, interested in learning more. 4, not important. And 5, not sure. It is completely fine if you are in the not sure category. After all, that is the subject of today's webinar. You only get to select 1 answer, so give it your best shot. And we'd like to get about 3/4 of the audience voting so that our panelists have an idea of what the relative interest and background is of the people listening in today. So we're pretty close. I'm going to give you about 10, 15 more seconds to get your vote in, and then I'm going to share the answers so that we can see what the interest levels are at. Okay, I'm closing the poll now and sharing the results. Very interesting. All right, we have 21% of the audience saying very important. We already integrate one or more solutions. 30% saying it's important and our integration planning is underway. 43% are interested in learning more. Well, we have a match. 1% say it's not important and 4% say they are not sure. Michael, how does this line up with what you were thinking?
It actually lines pretty well. What we're finding, and we spoke about this last week, is a CMMS and integrating that data is really just one piece of the bigger picture.
Mm-hmm.
Now, one thing that we probably should have clarified is when we're speaking of integrations here, are we speaking about an integration with, say, an ERP for purchasing, processing of invoices, or is it to an HR system for training, certifications, and payouts,
Mm-hmm.
as well as on the other side, again, integrating in condition monitoring data. Yeah, so integrating can mean a lot of things to different people, but specifically around the CMMS integration for condition data, as the reliability journey evolves for different customers, interested in learning more is predominantly how we work. Everyone's looking for what's that next step, how are we on the cutting edge of technology as we move forward, and I anticipate that this will grow even more.
Yeah, it feels like there's a lot of opportunity that our systems are finally primed to do some integrations, depending obviously on the situation in plant and what's most important from a business priority perspective.
Sure.
Any other comments, or should we move forward?
I think we'll press on.
Back to you.
All right, so where I'll hand it from here is actually over to one of my colleagues, Mike Ciocys. He is one of our, again, subject matter experts on the proof technique systems.
No, thank you very much. And yeah, so my kind of expertise here is talking about from the data connector side. How do we get some of these? What kind of systems do we have, and how do we get data into these systems? So let's take a look at some of the devices and talk about some of the details. So maybe if we can kick to the next slide here. So one that we have in the portfolio here is called the VibGuard, and this is a device that we permanently installed. And which is a little bit different than, say, the route collection or something that's handheld, that you're walking around and collecting data. We're talking about something that's now kind of fully dedicated to being installed. It's going to have some sensors on the machine, and its primary focus is to collect measurement data. And so that might be vibration, it might be speed, it might be load, it might be anything that's pertinent to the operation of that piece of equipment. And typically one of the kind of decision factors with, do you walk around and collect data or do you permanently mount something, is kind of these critical values. Is it high value? Is this thing really expensive? Is it hard to replace? Is a part of it hard to replace? And that could be true for a lot of different gearboxes. It could be true for something that's exotic. Maybe there's only one or two that you have in the plant, and having parts to replace it is very tricky, which kind of goes into, is it non-redundant? Like if you have many of them, there might be a different economic situation here to why you maybe want to monitor this in a different way. Its complexity is one of the biggest components, is that if this machine changes speed, changes load, has a different operating state, and you're kind of just hoping that the timing of, hey, I show up on day one to collect data, when I show up on day two to collect it again, is it in the same condition? Is it doing the same thing? And the big issue there is, if you're going to compare data, you need it to be under the same conditions so that the data actually means something. There's a level of consistency between when you looked at it once or twice. Because if something goes up or down, is it because there's an issue, or is it because the process changed? So complexity can add to the factor that, yeah, we need to have something that's watching it all the time so that we can kind of control the variables. The other component is it mission critical? This is sometimes the trickiest one, because in some instances, you look at the biggest machine in the plant, you look at the most expensive one in the plant, and they might be important to monitor, but you might miss the fact that the oil pump or something much smaller, maybe cheaper, it has a high level of criticality, because if it fails, something's going to go very wrong. But it isn't apparent that that is actually something you want to look at, and that you need to kind of take a look at the whole process and be like, maybe this bearing isn't expensive, but if it goes down, the whole thing goes down. And so those other items, redundancy, high value, complexity, might not make sense in the fact that something cheaper, smaller, and redundant is still mission critical, but I need to watch it. I need to know before it fails, so that I can actually take the corrective action. So when looking at systems like this, these are kind of the main focus points. And then to kind of go along with our webinar series here, you have something permanently installed, which means that it's watching all the time. And now we can take this data and we can start to move it to other places. So let's kick to the next slide here real fast. I think the best way to explain some of these systems is to take an example. So, and you can take a look at some of the capabilities here as well. So we have this machine, I think this is a dynamometer, but with this application, we're collecting data, but we have a really dynamic process. And so a couple of things are important here to look at. And one of the first one is like this level 1 data. It's like trend data. It's like a value. It's like watching the stock market kind of go up and down. It's plotted over time. And this can be one of the best indicators that something's going on, because you're just kind of plotting, looking for a baseline and then looking for a change. And so in this application here, with using the VibGuard device, very simple amount of data to collect. And you can take a look and actually see in this instance, the trend is rising. With level 1 data though, it's kind of this aggregate overall value. It's really hard to then pinpoint what exactly is contributing to this issue. So what can help is that you add some context. So if you're measuring speed as well, you can take a look at the speed of the machine. Is the vibration getting worse as the machine spins faster? Is the speed pretty consistent and the vibration still getting worse? This can help add context. Is the vibration happening at all when the machine is running? Which could be an interesting thing, is that you're measuring something that's actually coming from somewhere else. And so that can help you as well. And then the third or fourth could be some of these process parameters like torque and load, which we'll get into here in a moment. But what can really help, and with a device like this, is that you have some kind of onboard capability, some processing, computing power. Again, you can take this data and take it to another level, which would be like this level 2, be looking at like spectral data, like here in the bottom left. From this data, this can highlight specifically what is going on. So we take this trend, we use this to kind of indicate if we have an issue. We can then use the level 2 data to pinpoint what exactly is going on. In this case, we can take a look at the frequencies. We can identify here actually that we have a bearing problem. And so it's not related to maybe the motor, the gearbox, to the inherent frame of the machine. It's actually inherent to the bearing. And so that then empowers the person that's watching this or looking at the data, or is responsible for this machine, to say, with this information, I don't have to replace the whole thing. I just have to order a new bearing, to plan some downtime. And of course, that's nice to know at that level. If this happens over and over and over again, what is nice is to look at, I have a consistent failure, something that consistently happens. I need to figure out what this is, and then you can become proactive. So that's what empowers you with more of this data. But I think an important component to this is you can collect a lot of condition data. So we have a device here that can measure vibrations, but what else can we pull in? And this is contextual. And so in this case, we call these process parameters. There are other components to the machine that maybe we're not directly measuring, but we can pull into the data stream to use as a comparison. So I have some examples here. Mike, I don't know if you can kick the slide here. Yeah, so some of the common ones are like speed. So in this case, in this example, we were measuring speed. Temperature is another one, though you have to be really careful with temperature. It's usually very delayed. And so in some respects, if you're waiting for the temperature to increase to see something is going good or bad, it might be too late. Current, voltage, very useful, especially on electric motors. Is it working harder? Is your voltage supply fluctuating? Pressure, fluid level, chemical plants, processing of chemical processing, that can be very important. And then also process stage. Are you running a paper mill and you're running different thicknesses of paper? And so does that mean process today is I'm running very thin paper, tomorrow it's very thick paper? And then also something maybe a little more binary, valve position, open, close, maybe percentage. And then something even completely abstract is price. Does something completely out of the norm from what you're measuring actually have value or have some type of context in terms of your data? And that can be very helpful. So let's take a look at some of these process parameters and how we would kind of move these around. So we'll take a look at the next slide. And this is another example of like, how do we get process parameter? So we have this kind of two-stage compressor. We have a high pressure section, a low pressure section. Sorry, this is one compressor. It runs in two different ways. So it runs at a higher pressure and a lower pressure, pardon me. And so the operation of this compressor is going through a PLC, some type of controller. And so this unit can then kind of tell us what's going on, what stage of the machine is it operating in, what kind of pressure is that. What we can use is we can use the information there and communicate it to the VibGuard and add some context to the data. So if we take a look at this trend in the top right, we have kind of this blue and orange vibration trend, but you can see it's very segmented. This compressor is kind of cycling on, cycling off, cycling on, and cycling off. And the orange and blue are actually telling us it's operating in two different ways, higher pressure and lower pressure. And so when looking at this, I want to avoid comparing vibration that's happening in the low pressure time frame to the high pressure time frame, which means I need to somehow take this data and separate it out. And one of the ways to do that is actually with another diagram like here, this kind of scatter plot, is that we can actually take a look at where does the vibration kind of concentrate itself when it's running in the two different places. And so this OP, this operating kind of pressure 1, turns out when it's running at higher pressure, it vibrates a little bit more than it does in operating state 2. You can see 2 kind of has a wider range of vibration. The color here is severity. What's actually quite interesting in this context is that when it's in downtime, it actually has this little spot of red. There's something actually vibrating quite hard down there. And so in this kind of graphic, we can see that by separating the data out, we add context, we make it comparable, and we're also leveraging data coming from another system to help us with context. Now, the question is, how do these two systems talk together? And there's a couple ways we can talk about that. So Mike, if you can kick us to the next slide. So on the right-hand side here, there's a couple open protocols. Might be very familiar to a lot of our viewers here. Modbus is definitely one of them. MQTT is a little more recent. Profinet is a little bit maybe older. But these are open kind of languages. No one owns these, so to speak. So you can write some code that kind of follows this protocol. And if the system you're working with understands this code, then you have this ability to communicate between the devices. There's advantages to some of these. MQTT kind of operates on like a broadcasting type of familiarity. Modbus is more, it needs to know where it's going and where it's coming from. Same with Profinet. But what we can do here is that a lot of the tools in the field across different manufacturers and different disciplines can use these to communicate very dissimilar systems and communicate between them. And so like in this little plant-wide network here, we have kind of this whole plant. We have our compressor example from before, the PLC. We have some of these auxiliary sensors, maybe from something else that's operating in the plant. A couple things are wireless. And then we have a couple of these VibGuards that are watching the compressor. And so what we can do here is using this plant-wide network. In this case, it could be Ethernet. It could be wireless, like wireless Ethernet. But Mike, if you can click the slide real fast, what we can do is the PLC can then write over, say Modbus or MQTT. You can say, hey, I have some information. I can share it to these VibGuard devices, and this is kind of the path it'll travel. This might just be an example from the previous slide where I just want to know what operating state it's in. Is it in high pressure or low pressure? But you could take something else from somewhere else in the plant, like what the weather is outside, and compare that to the pressure that the compressor is running at. You can then start to interconnect all these components using these open protocols. And because they're open and understood, any system can kind of be written to understand that. Some of the most kind of unique ways to use this system, we'll take a look at the next slide, is you have all this information. I want to visualize it. I want to see what's going on. And so in a couple examples here, you might have, say, this very complex kind of a crane excavator drag line. You have some information about its speed. You have some information about its vibration levels. All of this kind of moving across these open protocols. And so you don't just have one system collecting all this data and getting it from all different places. And some of that might be the control system for the drag line. It also might be from the VibGuard that's collecting its own data. And so you have some speed here. This can be very complex. This is a nice graphic. You can kind of visualize what inside this drag line is actually moving and what's going on. You can have something more simple, like this little wind turbine example, and you have kind of some bar graphs, which you can just use from the live data you're getting from these devices in the field. So you have some RPM, you have different vibration components, you have power generated, which would most likely come from the wind turbine controller, knowing how many megawatts are being produced. Some stuff with wind would be wind direction, wind speed. Those could all help you kind of determine, do you make best power when you're directly in the wind or slightly out of it? Does the vibration of the wind turbine increase when the wind is faster or slower? These can all help you troubleshoot or investigate different performance characteristics. Or you just might have a simple motor and pump. You're interested in knowing the temperature of the fluid pumping through it. You'd like to know some of the vibration levels that are going on inside the motor. And all I'm looking for is just a moment where I can have an alarm sent. It gets communicated, and someone has to go out there and check it out. With these visualization systems and these open protocols, one component here is that most of the data being moved is integers, just numbers. And so some of the complex graphs, these time waveforms, these spectrums and frequencies, they're a little too complex to move over some of these protocols. And so you have to kind of use this as like a level 1 kind of notification, looking at trends and single values, and then kind of dive deeper on the backside into some of these more complex graphs that can be investigated from the system itself. One of the components here that I didn't show is like it could be as simple as a traffic light. You just have something that's green, yellow, red, and so if that could be on a control board in front of the machine for the operators to look at. It could be that simple. It does not have to be this complex. And so, but this is all kind of showing from an actual device collecting data, processing the data, taking in process parameters, using open protocols to move this information. This is kind of represents how these integrations into the data connectors are possible. So Mike, I'll kick this over to you here. I hope we're doing okay on time so far.
That's great.
Any
questions?
Yeah, we've got lots of questions. So one of the sorry about that. All right, so we have a number of questions. The first one was about the range of sensors available and how you decide what level of sensor, whether it's wireless or wired, excuse me, that is most applicable for your scenario. So how do you generally advise people in that situation?
It's a good question. I would say for a vibration sensor, you're going to look at the frequency that the machine is running at. And so the most important part is that if it's a high-speed machine, I need to make sure I pick a sensor that has a high enough range to make sure that it can see what is actually happening in the machine. It gets complicated with gearboxes. You have all these teeth interacting, and so the frequency gets very high. And so one of the first things with a vibration sensor is the frequency. And you want to get as high frequency as you can because that's where a lot of the faults will start. It'll give you the earliest warning. Now, if you have a sensor in mind, because that'll then kind of control, do you need to have one that's wired? Is the sensor in that range only available in a wired configuration? Or is what you're looking at, like maybe a simple motor and pump, does it operate in a range that many other sensors also operate in? So you might be able to do wired or wireless. And then how frequently you need to collect data might also factor into, you need something that's watching all the time, because maybe a wireless sensor is only going to ping it so often. And so those type of considerations are where I would start. With other sensors, if you're on some type of turbo machinery and you have prox probes, you need to make sure you understand that does that system power the probe? Are you scaled for the right voltages? And then also, are you able to from prox probes, are you able to make orbits? Is that what you want to see? And so can your system actually accommodate those type of measurements? And so from that, that's kind of the first place to start, is the type of machine, the frequency, and then the functionality of the measurement system.
Okay, and someone wants to confirm whether level 2 spectrum data can really be available at the sensor level.
At the sensor, it would be depend on the sensor. So in this case for the VibGuard does the processing. But if you have some different sensors with some logic on the actual sensor itself, it's very possible it could process its own signal.
Okay, I'm going to read this question out. It's a little bit longer. How would integration work for analog control systems or completely mechanical control systems in relation to information or other than using a time constant?
I think there's a couple of components there. I'll do my best
Yeah.
with this one. So analog systems. So some of the most common analog systems are the 4 to 20 milliamps, and there's still a lot of capability out there for systems to read and understand 4 to 20 milliamp. There's also a way of digitizing it. So there's a lot of modules, including like the VibGuard, for instance, can take a 4 to 20 milliamp. And you can take it in and digitize it and broadcast it back out as a Modbus or an MQTT value. For different circumstances, if you have a lot of equipment, there's a lot of different modules that will take in these analog signals, voltages, milliamps, different type of sensors that still are putting that out, digitize them, and then have that broadcast or available across Modbus, Profinet, or MQTT. And so it's very common for, say, like a temperature probe. If you have hundreds of temperature probes and they're all kind of maybe measuring out in millivolts or RTDs, you can then take a module, have all that data come into that module, digitize it, make addresses, and then you can take that and share it across the plant. So there's a lot of those modules that are making kind of the old systems still compatible with the new systems.
Okay. Several people want to know how many sensors are usually needed on one asset.
Ooh, good question. So there's a lot of best practice. If you're looking at typically you're measuring bearings on rotating machines. And so if you're looking at that, you typically want, say, like a horizontal and a vertical, maybe an axial. So if you want to kind of take it as far as you could go, you're talking about 3 positions on each bearing of a machine. In some cases, that's typically redundant. You can typically start to chew away a few of those. And so you might be looking at on larger motors or larger machines, because you're trying to get as close to the signal, you're trying to get as close to the defect of the machine as possible. And so if on larger equipment, you're going to want more sensors because it's not going to travel as far. On smaller little 25, 50 horsepower motors, you can probably do 1 or 2 sensors. And then it's going to be dependent on what's being driven. So if it's a pump, maybe 1 or 2 sensors. If it's a gearbox in many stages, that gets a little more complex. If it's a fan, many different support bearings, then it's going to be kind of case-by-case basis.
Okay, we've got a lot of questions, so clearly did a great job. I'm going to try to get a couple more in here. And then audience, we will roll back to these at the end or answer afterward if we don't have enough time today. There was a comparable question, Mike, on how many pieces of equipment can be supported by a single VibGuard.
It's going to be, so that's a good question. The VibGuard has some locations for speed, and that's sometimes the first thing you want to look at is if the machine changes speed, we want to measure the speed so we can normalize the data that's being collected. And so if you have a VibGuard like what was shown here, there's typically 2 speed inputs on that. And so if your machine is very dynamic, we're probably talking about splitting the VibGuard in half. Have a speed probe on one machine, speed probe on another, and then having, say, 8 to 10 sensors a piece. You can break it apart. We have a different module that's a little smaller, and you can then compartmentalize the project and say and put one of these little VibGuard compacts per machine, and that way you can have kind of just per section. But the VibGuard can kind of be split 4 ways. It's about the way it wants, with the way the measurements get taken, the way you can break the triggers and the alarms, the way you can kind of delegate channels. Splitting it about 4 ways is about the max. And so, and then if you needed to do more machines, you just add another device.
All right, The last question I'm going to sneak in here is about the CMMS integration, maybe just a recap from what I'm seeing of what it looks like to have the VibGuard integrated with your CMMS as far as a usage model.
Yeah, so I'll cover this from my side, from the data collection side. So
Right.
the real goal with having it integrated into the CMMS is that if you're collecting this vibration data, you're collecting some type of process parameter, I'm looking for something that's going to indicate I need to take an action.
Mm-hmm.
And so you want to see if a trend increases. Then if something's going on, the trend might not give you exactly what's going on, but the vibration is increased. I maybe get an alarm. And maybe what I want is that I want that alarm to be processed on the CMMS side as a work order. Go investigate the machine, check it out, check the coupling. And so that level of, I'm kind of skipping the middleman, so to speak, is that I want the device to kind of take some action for me and instigate an action on the CMMS that then will dispatch somebody or notify somebody.
Right.
You could take it to another level that if it knew exactly which bearing was failing, that it would order the bearing for you.
Perfect. Okay, that answered a couple different questions. Let's roll on, and then we'll come back as we have time.
Sure.
All right, Brandon or Brian, I'll hand off to you.
Very good. Thank you very much, Mike. I appreciate it. So before we get started, just kind of backtrack. For decades, companies have recognized the value of real-time data like SCADA, PLC type source data flowing into the manufacturing execution systems. So some of us may refer to these as an MES, but let me say that again. So for more than a couple of decades, we've literally been leveraging this data, and we've been using the information coming from these data sources using readings like throughput or runtime in order to pull materials and help build out inventory so that we're realizing efficiencies coming out of our supply chain. So much so that the best practice in this were actually set in stone back in 1995 in ISA 95. What's relatively new and relevant to our conversation today is the idea of using this same data to manage and extend the life cycles of these exact same assets and equipment, as well as all of the support pieces and every piece of that supporting infrastructure, assets and equipment across the enterprise. Can you go to the next slide for me, Mike? So to kind of touch on something that my colleague Mike had touched on earlier in his presentation, is it's not always just the level 1 critical assets we're talking about. Sometimes it's the assets that could be part of, level crit 2 or level crit 3, that they're part of a system or even a subsystem that actually feeds to something more important. So if you look at the slide over on the right-hand side, in some cases, we could be talking about meter points that could be pressure, temperature, they could be throughput or production, could be runtime, but every one of those meter points may have a different level of importance, even if you're talking about a specific asset. So we want to treat each meter point uniquely. So, something like runtime, we may want to get that type of information every 24 hours or every 48 hours, because it's usually pretty simple math that informs what our thresholds are. When we want to trigger either an investigation or assessment on an asset, or if we want to trigger a piece of work to be done. But when we think about things like vibration or pressure or temperature, those can be a little more fluid in nature. So we may want to monitor those a little more consistently. Instead of every day, we may want to look at those every couple of hours so that we have a sense of how the asset's performing and what kind of condition it's in. So when we think about Connect2Assets, think of it as kind of a bridge with dozens of on-ramps that can handle any volume of traffic without issue. So you could have hundreds, if not thousands, of vehicles that are getting on, or vehicles meaning data points, and maybe only about 15 a day may actually have some meaning to operations. So those are going to be the only 15 bits of information that need to go to the CMS, because it's going to inform an action, or it's going to make somebody take a decision with some level of criticality or some level of urgency that we need to be made aware of it today and in real time, because that's going to change how we behave in our current shift. So at the same time, there can be tens, if not hundreds of thousands of other readings that are coming through, and all they're saying is that everything's okay. Everything's operating the way it's supposed to, everything's within normal parameters. So that information is important, but it's not critical in nature. So what we try to capture is a trail that's a proof point So you can look back in the CMMS system and you can say at this date, at this time, we know for certain that this piece of equipment, this meter point, was operating the way it's supposed to, and everything's okay with it. So that when we have a deviation from that or a change from normal, we can look back and say, you know, through reverse traceability, when's the last time that we know the asset was operating okay? And maybe there's some other indicators we can look at from an RCA perspective to determine when we started to deviate or start to see performance degradation. So that when we have a status change, we're notifying our CMMS system immediately without anybody having to do anything different. So when we talk about integrations like we are today, traditionally with this type of integration, there's been two major roadblocks to the technology. And the first one of that is normally we view integrations inherently as risky. You know, generally speaking, when we talk about a CMMS or an EAM integrating to another system, we are talking about the ERP or the HR system, like my colleague Mike Mills had indicated. But integrations are generally viewed as being expensive, complex, so that when we do them, you know, if one of those systems that's touching upgrades, usually we expect to be some kind of negative impact to what that integration is. And with that, we assume rework, we assume more customization to one or two of the systems in order to keep that bridge of data flowing. So the ability to deploy these data bridges in hours and days versus weeks and months is a differentiator. And it's something that for the Fluke solutions we're talking about today is something that we've really taken into account so that we're able to deploy out of the box in that when we have those deployments done, they're stable so that as systems upgrade, there's not a negative impact, so that they're more stable in the form of there's not a lot of risk in terms of downtime. And when you upgrade, the data flows are able to continue. And we account for, you know, the roadmap so that as things extend out, as new systems are added, as new data on-ramps are added to the bridges, that those are supported in a proactive basis. Another roadblock when we think about integrations to these systems, particularly when we talk about SCADA PLC systems, is that there's really no standardization. In more than a decade of doing these types of projects, I've yet to encounter a single operation that uses one single type of SCADA or PLC protocol. For most of us, it's a combination of three or more. So for instance, you could do Modbus, Siemens, or Allen Bradley. And in a lot of cases, you'll have 2, 3, sometimes I've seen as many as 12 different protocols deployed at a single site, because when we're outfitting our operations, we're not thinking about standardizing those communication protocols. Specifically, we're talking about fleets that, you know, have been around. So another thing that's becoming more common instead of integrating the CMS is as organizations start to look at these different systems that are disparate, they start to look at porting them into other third-party systems that allow them to log in and view how assets are performing and see these meter points presented in a UI. The challenge there is that you're still requiring somebody to go in, log into a third-party system, know what they're looking for to go over the data, and then when they find something that's meaningful, they then get to pivot and log into a CMMS system and enter either a work request or some kind of initiation for a technician or a planner scheduler to go out and take a look at what needs to be done at the asset. So what Connect2Assets does is we focus on automating that entire process so that from the moment that an asset event happens, we're notifying in less than 10 seconds the CMMS or the EAM system that there's been a change of status at the asset. So we're not just taking the data, but we're routing it to the right person. So the right information is getting to the right person in a timely manner. And as this happens, it's happening without the need for an asset owner to notice something or someone to walk by a piece of equipment or a route-based PM technician to actually pick up on whether it's an odd smell, a noise, perhaps a rise in temperature that they're able to detect. And instead, we're having all of that monitored in a 24/7 basis. And the important piece of that is that integration to the CMMS system, because it's automating that entire process from what could take minutes, hours, sometimes even shifts. It's happening again in less than 10 seconds from the moment that that change in status occurs to the moment that somebody's being notified. Can you go to the next slide for me, Mike? So when we talk about the value of condition-based maintenance like this, it's really the ability to care for our assets and equipment based on the actual real-time condition. So if you look at the KPIs that we have on the right side of the screen, these, generally speaking, align to what you would expect with something like condition-based maintenance. Starting at the top, the reduction in calendar PMs, if you have 3 lines that are identical, similar configurations, same actual assets that make them up, same processes, but if you have one that's operating on a 24/7 basis, another one that's operating 5 days a week, and then a third that's used primarily for peak demand times, there's not a lot of logic in maintaining these identically. Instead, the ability to pull back and actually look at how often are we using that equipment, what is the actual current condition of the equipment, what is the asset telling us it needs, versus saying, okay, it's been 8 months, it's time to go tear that apart, replace these consumable parts, relubricate, retighten, and get everything off and running. That type of value really isn't a big thing. And we'll touch on the next slide in terms of the costs that are hidden in that. But the ability to reduce calendar PMs and start treating the equipment based on what it actually needs is a huge value add for organizations. Now, when you get into some regulatory orgs and operations, there's always going to be some parts on critical assets that we are going to stick with calendar PMs. So we're never going to abandon the concept of calendar PMs 100%. There's always going to be some pieces we do simply to help us manage risks as organizations. But by and large, when you talk about level 2 and level 3 critical pieces of equipment, the ability to pull back and start acting logically in terms of how we maintain our assets versus doing what an OEM manual told us can present phenomenal savings for organizations. The other piece of this is taking the readings from the assets and equipment does more than just tell a technician or a manager, hey, we need to go do something. It gives them context so that when a technician actually gets out to a piece of equipment, just in travel time alone, they're able to understand what they're walking into and anticipate to some degree what the scenario is. And what that means is they're able to quickly diagnose what's actually happening at the equipment when they're there, which also informs their ability to reduce the mean time to repair. And when you look at things like MTTR, that immediately informs things like asset availability or even OEE, overall equipment effectiveness, because the ability of a technician to walk in, instead of walking into kind of a blank slate of, I don't know what I'm doing, but I have a work order here that says I'm supposed to be at this piece of equipment. Maybe I have a kit with me, but I'm not real clear on what the issue is. The difference there is a step change, because instead they're walking out again with context. So the simple integration of the asset data telling a technician, okay, you need to be out there and here is what you're expecting. They can understand immediately, is this an electrical issue? Is it mechanical? Is there something else that I know I'm going to be walking into that maybe instead of 100 possibilities, boils it down to 10? And when we think about the impact that this has, it's really kind of across the board. Traditionally, organizations have suffered from this view of anything with MRO or maintenance repair operations is more of a cost center than a profit center, is starting to be defeated with information like this, because we're understanding that availability of our assets and the effectiveness of our assets, as well as our technicians, directly informs our ability to be productive as organizations and honor the missions that we're all on the same team for. So when you think about the information we can pass to technicians through these integrations helps inform their ability to stick within HSE protocols, the sustainability of our assets, and ultimately extend the life cycles of our assets that support and drive the missions that we're all on. Can you go to the next slide for me, Mike? So we talked about the cost of failure, as well as in some cases, the costs that go into us over maintaining our assets. So if we look here, the costs associated with failure is something that we are all familiar with. A lot of us probably know what an hour of unplanned downtime would cost our organizations. A slightly smaller number of us can probably tell us what the hidden costs of unplanned failures are. These are usually learned from very specific and painful experiences. I myself have been a part of a number of them. These often can include things like premium charges associated with express shipping, overtime costs. They can also result in peripheral costs though as well. And these can include things like a failure to meet our commitments to external customers. These can also increase our backlogs to our internal customers. But beyond these costs of failure, while we call these out a lot, I also do want to talk very briefly on the costs associated with over maintenance. Because every time that we do a maintenance activity, that's not necessary by nature. We take apart an asset, we're introducing risk. Did we properly lubricate it? Did we tighten the bolts and screws? Did we use the right consumable parts? I worked with the refinery years ago, and they talked a lot about a specific case where they started with the washer on this application that was initially a very small, cheap plastic piece. And as calendar PMs got triggered, they would go to stock. Technicians would choose the next best available part because that particular part was out of stock. And suddenly one day they had gotten to the point where they were using a $40 washer where it should have been a 20-cent piece. And it's just something that happened with people meaning to do the right thing and just kept defaulting. And the whole thing triggered because they were doing maintenance in just kind of an out of mind way. At another group that I'd worked with, there was a reliability director, and he talked about he always wanted his new employees to review and revise the job plans. And the idea there was that someone who'd worked there for 10 years and done the job 100 times, they'll skip steps in their head. They'll do things out of muscle memory. Whereas someone who's new is more likely to document every single detail associated to an assignment. And the things that I want to talk about there just briefly again is the value of maintaining when we need to versus doing it just kind of out of muscle memory, because there are a lot of costs, and we're introducing risk in our organizations by continuing down the path of saying every 2 years we need to do this, or every 6 months we need to do that, when there's not a lot of logic and the asset's telling us otherwise. The asset's telling us, no, I've got another few months in me before we need to do this. And that doesn't just translate to savings, it translates to, again, extending the life cycle of the asset itself. You can go next slide for me. All right, I believe this goes into Jeremy.
Yes, it does. Leah, any questions?
So you covered a lot of the questions, I think, as you got into more of the cost and ROI discussion. There's one more question that's pretty important I'm going to ask, and then we'll go into Jeremy. And audience, thank you for the level of your questions. Really good stuff, and we will get back to you afterward, if not at the end. So Brian, the question for you is about the level of skill that technicians need to have. So when you integrate asset data into your CMMS, and then that level of information coming to the maintenance technician, do they need to be upskilled at that point, or can they? What level of training is required?
It's a very good question, and it's actually not a lot, because when you talk about the SCADA information, when we talk about automation systems, it can be a little daunting. But the truth is, what we're doing is we're taking information from the asset and we're putting it in the hands of the technician in a meaningful way and using the CMMS to translate. So they're not just being told, a binary code of something that's happening. They're being given context by the CMMS of what the asset is, what the reading is, what that means to them. So it's actually zero training on that part. But at the same time, it does allow the technician to gain another level of value for themselves to the organization, because it's giving them more flexibility and making them a little more dynamic.
Great. All right, Jeremy, let's move on to you.
Good morning, everyone. Like she said, this is Jeremy Go. I'm a solutions engineer here at Fluke, and today I'm going to talk a little bit about how you can leverage all the data you are collecting from your Fluke tools to better understand the condition of your assets. Fluke Connect is a central repository for all the measurement and condition monitoring data that you're collecting via routes and sensors in the day-to-day management of your assets. And the key to this is really being able to easily assign, track, and trend your measurements so you can get an accurate picture of your assets condition over time. Now, primarily these measurements are coming from Fluke handheld tools, as well as our condition monitoring sensors. Now, first, let's take a look at a few of the most popular tools today. Mike, if you wouldn't mind moving forward with the slide, please. So first up, we have our thermal imagers. Now, temperature data can be a powerful tool to catch one of the leading indicators of asset failure, and thermal imagers make acquiring this data really easy. Fluke has a wide variety of Fluke Connect enabled thermal imagers available to provide your teams with an easy way to gather this data. You can link it to your asset records and you can track it over time. With Fluke Connect Desktop, it's also equipped with our Smart View software, which will allow you to work with and edit your thermal images right there in Fluke Connect. You can assign them to asset records, you can comment them, and you can create reports with them. So all of these images can be easily uploaded to the cloud through the Fluke Connect software that happens right through your mobile phone, or they can be downloaded directly to your computer and then uploaded through the Fluke Connect desktop software. Might be a more traditional process for some of you. Mike, can you move forward, please? Next up is the Fluke Connect measurements aspect of our system. Now, route running with handheld tools is standard practice for most facilities today. Individual measurements taken alone have limited value for a predictive maintenance program, but being able to take this data, assign it to your assets, and trend it over time can allow you to leverage the routines and behaviors you're already doing to help you get ahead of those critical asset failures. Fluke has a variety of connected handheld tools available for your teams. Near the top of that failure curve is vibration, and the handheld Fluke 805 vibration meter is an easy to use connected tool to monitor vibration while running routes. And combining that with Fluke Connect, you can upload your measurements taken, you can assign them to asset records, and trend that vibration data you're taking over time. This makes it an easy process to identify when your assets are trending towards failure. From there, you can leverage our vibration analysis tools or laser alignment tools to solve your problem before it becomes a catastrophic failure. Fluke Connect measurements also allows you to use our Fluke Connect enabled digital multimeters, clamp meters, and thermometers to take measurements, assign them to assets, and trend them over time, giving you other helpful indicators in the health of your assets. Next up is our Fluke Connect condition monitoring. Now, while running routes and taking periodic measurements are the standard of how things are done today, the next step towards true predictive maintenance is condition monitoring. Fluke offers several sensors to assist you in this journey. The 3561 vibration monitors will provide you with triaxial measurements along with temperature every 2 minutes. This means you'll be able to get an accurate trend of vibration data coming from your assets far more frequently than you would with traditional handheld tools to help you ensure you are aware of asset health changes the moment that they occur. The 3543 phase power monitor will allow you to monitor power performance of your assets with data reporting every minute. Because Fluke Connect condition monitoring is constantly streaming this gathered data to the cloud, monitoring sessions are no longer limited to a few days or weeks, but instead they can be run indefinitely. Coupled with the alarms and push notifications provided by our Fluke Connect condition monitoring, your teams will be aware of potential problems and can plan to resolve them when it's most convenient for your operations. Next slide, please. Now, in the end here, the goal is to achieve predictive maintenance of your assets. And it's like you're going to be using a combination of several tools and collecting multiple data points. Managing all of this data can become a difficult task on all of it by itself. By utilizing the Fluke Connect platform, you can make this job easy. Now, Fluke Connect allows you to take all of this handheld tool data along with your condition monitoring sensor data and compile it into one central database. From there, you can assign it to assets. You can easily view visual trends and graphs, which the software makes for you. And this central database also makes it exceptionally easy for you to leverage all of this data and share it with your CMMS so that you can integrate and utilize that data to create things like work orders and get ahead of these issues and keep track and record of all of that. Any questions?
Because we are a little short on time, I think we're going to roll right into the final portion, and then we're going to follow up with you afterward, Jeremy, okay?
Sure.
Sounds good. I'll take it from here. Thanks, Leah. Thanks, Mike, Brian, Jeremy. So we've been speaking for the most part on the data connectors and collectors side of the system, which are gathering data from hardware and sensors, right? But what does this have to do with your computerized maintenance management software? Okay, and how does this fit in with the earlier thought of connected reliability? Well, members of Fluke Reliability looked at this over the years and said, well, it's great that we have all of this data, but how do we take this data to the next level? Wouldn't it make sense to have this go somewhere so that when you receive these alerts and alarms, that you're able to pull up the profile for an asset? And so it became one of the first pillars of that connected reliability ecosystem, where you can join data connectors and enterprise connectors, such as the CMMS. So now that we know that that we have all this condition data, we know that by itself it's incomplete. When an asset raises its hand and says, I think I'm having an issue, it doesn't know when the asset was last serviced. It doesn't know what actions were performed or when the maintenance is next due. It doesn't know an asset's history of failure, what parts are needed to complete specific jobs, and whether those parts are currently on hand. And in a survey that we conducted a few years ago, 84% of all teams had mentioned that they don't have access to condition data in the CMMS, and 71% said that they don't have an aggregated view of asset health as a whole. Someone described this to me as, you have all the players for a certain sport, but without having that condition data in with your CMMS, it's like you don't have a playbook. So the goal with valuable data is to use it to drive action and enhance and improve upon those actions to increase the life of your assets. So what we should be looking to do is, close the gaps by uniting that real-time condition data with your organization's system of record for asset management, and where asset health and history information and descriptive information is usually kept. So I know in the essence of time here, really to sum up, over the past 2 sessions, we've covered ways in which to get more value from your CMMS, whether it's using existing functionality to control costs, provide value to your enterprise systems, and now also the ways in which to use condition and telling data to drive efficiencies and move to more of a predictive space. Obviously, as I hand off to Leah here, if there are any questions on what we've covered to date or what the integrations look like between these products and the eMaint CMMS, please do not hesitate to reach out. We're happy to assist.
If you want to forward to your next slide, I think that your email, yep, there we go. So audience, you are welcome to contact Michael directly, and he can forward on questions to everyone else on the panel today. Some of your questions we will definitely be following up with you directly afterward. Great questions that you asked. I know we covered a lot of information today. Part 1 of this presentation is already available on Excelix.com. Part 2, today's, will be uploaded probably by tomorrow. You're welcome to go back through. But for right now, I'm going to have you forward on to the next slide, Michael. Please tune in for our next session on April 7th with Calvin Williams. He is one of the most sought after trainers on continuous improvement strategies. Really, really good stuff. You can find examples of his work on LinkedIn if you're curious, but I really hope you'll be able to join us for the live session. The coaching and learning on this is going to be tremendous, and you'll find more information on that on Excelix.com as well. And then one more forward, if you would please, Michael. I want everyone to stay online for a moment after I close the webinar, because there's going to be a brief pause and then the survey link will appear, and we really appreciate it when you can answer those questions, give us feedback on how today went and what else you'd like to see in this webinar series. Let us know if you want to get a certificate, and then we'll send you a copy of today's presentation as well. So with that, I want to thank all of our presenters today, Mike and Brian and Jeremy and Michael. This was tremendous. This was a lot of information. I feel like we could keep talking about the integration into the CMMS and what it looks like from the CMMS part of view. So maybe we'll have a part 3, who knows? But thank you very much for joining today.
Yeah, thank you so much for having us.
Thanks for having us. Look forward to speaking to everyone soon.
All right, and with that, I'm going to close out today's webinar, but stay tuned and come back for the next time.